Surprisingly, the Earth's net energy gain from the sun is effectively zero, as it radiates back into space an amount of energy equal to what it receives. The true life-sustaining gift from the sun is not energy quantity, but its low-entropy quality, arriving as concentrated, high-frequency photons. This process reveals that life thrives by consuming low-entropy energy and exporting high-entropy energy, a fundamental principle of thermodynamics. The thermodynamic origins of entropy are rooted in the Industrial Revolution's quest to understand the fundamental limits of heat engine efficiency. French engineer Sadi Carnot conceived of an idealized, frictionless engine to determine the theoretical maximum work that could be extracted from heat. His work revealed that some energy is always lost as unusable waste heat, laying the groundwork for the concept of entropy as a measure of energy's unavailability for work. The Carnot cycle illustrates these theoretical limits by modeling a perfect, reversible process involving four distinct stages of gas expansion and compression. It demonstrates that the maximum possible efficiency is not dependent on the working substance, but solely on the temperature difference between the hot source and the cold sink. By showing that heat must be discarded to the cold sink to complete the cycle, it establishes an unbreakable upper bound on efficiency for any heat engine. The formula eta_max equals 1, T_cold/T_hot, reveals the fundamental truth that converting heat into work can never be 100% efficient. It dictates that efficiency is inherently limited by the temperatures of the heat reservoirs, measured on an absolute scale like Kelvin. This equation proves that a temperature differential is essential for work extraction and that some energy must always be discharged as waste heat to a colder reservoir, a core tenet of the second law of thermodynamics. Entropy was first defined mathematically by Rudolf Clausius in the 1860s to quantify the concept of irreversibility in physical processes. He proposed that the change in entropy, delta S, measures the amount of thermal energy, delta Q, transferred in a reversible process divided by the absolute temperature, T, at which the transfer occurs. Fundamentally, entropy measures the dispersal or spreading out of energy, quantify how energy becomes less concentrated and thus less available to perform useful work. Real-world processes proceed spontaneously in one direction due to ubiquitous irreversible effects like friction, heat dissipation, and diffusion. Unlike idealized reversible processes, these phenomena distribute energy in a way that makes it unavailable for work, preventing the system from returning to its initial state on its own. This unidirectional flow, known as the arrow of time, is a direct consequence of the second law of thermodynamics, which states that the total entropy of an isolated system always increases during a spontaneous process. Clausius's definition, delta S equals delta Q/T, precisely measures energy dispersal by relating the heat transferred to the absolute temperature at which it occurs. Adding a certain amount of heat to a cold system causes a much larger entropy increase than adding the same heat to a hot system, reflecting a more significant relative energy spread. This formula quantifies how energy becomes more diffuse and less useful as it flows from hotter to colder regions, providing a concrete metric for the increase in total entropy. A statistical perspective, pioneered by Ludwig Boltzmann, redefined entropy not as a deterministic property of energy flow, but as a measure of probability and microscopic arrangements. He connected the macroscopic properties we observe, like pressure and temperature, to the countless possible microstates or configurations of individual atoms and molecules. This revolutionary view transformed the second law of thermodynamics from an absolute decree into a statement about overwhelming statistical likelihood, explaining that systems evolve towards their most probable states. The fundamental laws governing microscopic interactions, like the collision of two particles, are perfectly time-reversible and look physically plausible when run backward. Macroscopic phenomena are irreversible because they involve an immense number of particles, making a spontaneous return from a high-probability state to a low-probability one statistically impossible. The perceived arrow of time emerges from this statistical certainty. While a reverse process is not forbidden by physical law, it is so fantastically improbable that it is never observed. Maxwell's demon, a hypothetical being that sorts fast and slow molecules without work, challenged the second law by seemingly decreasing entropy in an isolated system. This paradox suggested a violation of thermodynamic principles, as the demon could create a temperature difference and thus a potential for work from a uniform gas. The resolution lies in information theory, revealing that the act of acquiring information about the molecules and erasing it from the demon's memory necessarily generates more thermodynamic entropy than the sorting process reduces. Boltzmann's equation, S equals K asterisk ln W, provides a direct mathematical link between the macroscopic property of entropy, S, and the microscopic world. It defines entropy as proportional to the natural logarithm of W, which represents the total number of distinct microstates or atomic arrangements corresponding to a single observable macrostate. This formula establishes that a state of high entropy is not one of disorder, but simply one that is vastly more probable because it can be realized in an astronomically larger number of ways. A gas spreading out is not driven by a mysterious force towards disorder, but by the simple laws of probability applied to a vast number of particles. The number of possible microscopic arrangements for the gas molecules being distributed throughout the entire container is astronomically larger than the number of arrangements where they are confined to one corner. Therefore, the system's evolution toward a uniform distribution is a spontaneous transition into the most probable state, a configuration with the highest number of accessible microstates, and thus the highest entropy. The relationship between thermodynamic entropy and information is profound, as both concepts quantify a form of uncertainty or missing information. Thermodynamic entropy reflects our lack of knowledge about the precise microstate of a physical system, while information entropy measures the uncertainty about the content of a message. This deep connection is physically manifested in Landauer's principle, which states that erasing information inevitably increases thermodynamic entropy in the environment. Shannon's information entropy quantifies unpredictability by measuring the average amount of surprise associated with each piece of data. A data set with high redundancy and predictability, like a repeating pattern, has low entropy because the next element is rarely surprising. Conversely, a random sequence has high entropy because each new element is highly unpredictable, carrying the maximum amount of new information. Landauer's principle establishes that the erasure of information is an irreversible process with a real, physical cost. It dictates a minimum amount of energy that must be dissipated as heat into the environment for every bit of information that is logically erased. This principle forges a fundamental link between information theory and physics, proving that reducing information entropy within a system requires a corresponding increase in the thermodynamic entropy of its surroundings. Life's remarkable complexity can exist because living organisms are open systems, not isolated ones as described by the simplest form of the second law. They maintain their internal order by continuously exchanging energy and matter with their environment, a process that does not violate universal entropy increase. This constant flow allows life to build and sustain intricate structures, effectively creating pockets of low entropy at the expense of a much larger entropy increase in their surroundings. Biological systems maintain their high degree of order by functioning as non-equilibrium systems, constantly processing energy from their environment. They effectively eat low-entropy energy, such as sunlight or chemical bonds in food, and use it to power the creation and maintenance of their complex structures. In doing so, they export high-entropy waste, primarily as heat, ensuring that the total entropy of the organism plus its environment always increases, thus perfectly adhering to the second law of thermodynamics. Dissipative structures, a concept from Nobel laureate Ilya Prigogine, are ordered patterns that spontaneously emerge in systems held far from thermodynamic equilibrium. When a system is subjected to a continuous flow of energy, it can self-organize into complex forms like hurricanes, chemical clocks, or even living cells. These structures are incredibly efficient at dissipating energy and producing entropy, suggesting that the formation of order can be a natural consequence of accelerating the universe's overall trend towards greater entropy. Entropy shapes the entire timeline of the universe by providing a clear directionality, known as the thermodynamic arrow of time. The universe's past is defined by the past hypothesis, a state of remarkably low entropy at the Big Bang, which provided the potential for all subsequent complexity. Its present is characterized by the ongoing increase of entropy through structure formation, and its distant future points towards a heat death, a state of maximum entropy where all processes cease. Counterintuitively, the smooth, uniform plasma of the early universe represented a state of extremely low entropy precisely because of gravity's influence. In a self-gravitating system, a uniform distribution is a highly improbable configuration, as gravity naturally pulls matter together into clumps. The high entropy, or most probable, state for a gravitating system is a clumpy one, consisting of stars, galaxies, and black holes, making the initial smoothness a vast reservoir of gravitational potential. Supermassive black holes are considered the universe's most entropic objects because they represent the ultimate endpoint of gravitational collapse, packing immense mass into a small region. The Beakenstein-Hawking formula reveals that a black hole's entropy is not proportional to its volume, but to the surface area of its event horizon. This enormous entropy signifies the colossal amount of information about the matter that formed the black hole, which is now inaccessible to outside observers. The concept of a final heat death of the universe describes a future state of maximum entropy, where all energy is uniformly distributed and no temperature gradients exist. In this state of perfect thermodynamic equilibrium, no work can be done, no complex processes can occur, and nothing of consequence can ever happen again. This ultimate equilibrium implies that the arrow of time itself would cease to have meaning, as the forward direction of time would become indistinguishable from the backward direction without the constant increase of entropy to define it.